Okay, hello everyone. Let's go ahead and take a look at Chapter 8, Section F, which is called the binomial expansion. Now, let's go ahead and just make sure that we know exactly what we're referring to when we talk about first a binomial and then an expansion. Let's just go ahead and take a look here at this particular value in the parentheses, and it says a plus b. Now notice that's called a binomial. And a binomial, by definition, is the sum of two terms. So notice this is the first term, and that's the second term, and notice that they're added together. So that's what we call a binomial. Now what are we talking about when we talk about an expansion? An expansion means, say for example, that we have, well, this is to the 0 power, this is to the first power, which we know of course would be 0 and a plus b respectively. And then we have, say for example, a plus b quantity squared. Now, of course, if we use FOIL, we can very easily come up with the result a squared plus 2ab plus b squared. And I'm hoping that everybody can do that in their head. So this is what we mean then by expanding it. By taking a look at this, this is going to be your factored and simplified form of this, which is the expanded form that is equivalent, of course, to this. So let's say, for example, we wanted to find out what this binomial a plus b is. And say, for example, we raised it to the third power. What would that expansion look like? What if we did it to the fourth power? What if we raised the binomial to the fifth power? How do we go about finding that expansion of the binomial raised to a positive integer exponent? That's what we're referring to when we talk about the binomial expansion. Now, how do we go about doing that? Again, as I mentioned before, I think if we take anything to the 0, 1, or 2 power, any binomial raised to the 0, 1, or 2 power, it's going to be very easy, and we already have techniques to be able to do that. Well, what happens when it gets to things? What happens when the exponent becomes an integer that is larger than 2? Okay, so before we go ahead and describe how that comes about, let's go ahead and take a look at something that's going to be called Pascal's triangle. Now, Pascal's triangle, let me move this over. Pascal's triangle looks like this. Now notice it's a triangular array of numbers. And what we start off is with the value of 1. What happens then is that on the next line I go 1 and 1. And then on the next line it's 1, 2, and 1. Now why is it 1, 2, and 1? Well, notice that all of the outsides, the edges, the outside edges, these two outside edges of the triangles, they're all 1s. Okay? How do I get this 2? Okay? Well, take a look. Okay, let's see if you can figure it out. Notice that the next line says 1, 3, 3, 1. And let's see if you can figure out how I got the 3 and this 3 here. Now notice the next one is 1, 4, 6, 4, 1. The next one is 1, 5, 10, 10, 5, 1. Okay, so hopefully you can see a pattern there. Do you? Okay, well maybe you don't. If you do see it, hopefully you recognize that this number here is really the sum of the two numbers that are above and to the left and right of it. So this number here is the sum of 6 and 4. This number here is the sum of 3 and 3. This number here is the sum of 3 and 4 and 3 and 1. And so forth. And you can continue to generate this pattern all the way through. So let's say, for example, that n is equal to 6, and I'll tell you why it's 6. Here's 1. This one, of course, should be 6. This, of course, should be 15. This is 20, 15, 6, and 1. Now, what is the relevancy of this here with regards to our original question about how do you expand a binomial raised to a positive integer exponent? So let's take a look at this here. Now, I'm going to go ahead and just focus on these numbers here. Okay, the 1, the 1, the 1, 1, 2, and 1, because we already know where those numbers actually go here. So let's take a look. 1, here's the 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 2, and here's the other 1. So notice that there's a relationship between the way that this triangle is progressing, this progression of numbers, with the expansion of the binomials. So I would assume then that for 3a plus b raised to the third power, it'd have to go 1, 3, 3, 1. And sure enough, it does. It goes 1, 3, 3, 1. If I take a look at the fourth power of a plus b, then I got 1, 4, 6, 4, 1. If I do it the fifth power, notice it's 1, 5, 10, 10, 5, and 1. And of course I could continue if I wanted to. Now, that doesn't help us yet with the expansion because I'm not exactly sure how to get the a values and the b values. So notice that what we have here is a very interesting pattern with regards to how the exponents are actually going about. So, in this case over here, let's start off with this one here. Notice that it's a to the first. In this case over here, it's a to the second. And this should be a to the third. This should be a to the fourth. And this should be a to the fifth. Now, notice that as I go down, this, the value of the exponent for a is always decreasing by 1. So notice in this case, even in this case over here, the next value is actually a to the 0, which is 1. So notice in this case it's a to the second, a to the first, a to the 0. So in this case also it's going to be a to the third, a to the second, a to the first, and I'll go ahead and write it as a to the 0. In this case over here, a to the third, a to the second, a to the first, a to the 0, a to the fourth here, a to the third, a squared, a to the first, and a to the 0. Now I'll do this in a different color so we can keep these things separated here. Now take a look at the b's. The b's actually start off with 0, like b to the 0, and then every time that we move to the next term, the value of the exponent increases by 1. So notice that this is the same thing as b to the 0, this is b to the first, b to the second, and b to the third. Oops, sorry. B to the third. Can you see that? Oh. Okay, b to the third. And then notice in this case over here, it's b to the 0. This is b to the first, b to the second, b to the third, b to the fourth. In this case over here, it's b to the 0, b to the first, b to the second, b to the third, b to the fourth, and b to the fifth. Okay, and of course notice that since this is just a and b added together, all the values which join these are all pluses. Okay, so there you go. Now, so long as I have Pascal's triangle, I can now always go ahead and generate the expansion of any binomial raised to a positive integer exponent.